In this video, we are going to talk about how to find derivatives of different functions, and the remainder of chapter 4 is going to be how to find derivatives of different types of functions. And so this section, the first section, is really just kind of the basic rules, the basic functions that we can look at. Um, Now, the first thing to remember, we've talked about derivatives, and hopefully you're familiar with what a derivative is. Just to refresh your memory, a derivative is referring to the instantaneous rate of change. So the instantaneous rate of change, if you prefer, you could think of it as the slope at any given point. So anytime you have any kind of curve, if we look at any point on this curve and we consider the tangent line, what is the slope of that tangent line? That tells us what the derivative of the function is at that point. And so it's useful to be able to, given any particular function, find the derivative of that function, and then you can find the slope of the tangent line at any point of that curve. And so there are many ways to write the derivative. The way we've seen is using this f prime notation. So that little apostrophe there we read as prime. So we'd read this f prime of x. Another common way is to write dy over dx. This is just referring to the change in y over the change in x, which goes back to slope. Remember from algebra, the slope is measured as rise over run, or measured as the change in y over the change in x. We use this d. This is referring to the instantaneous rate, whereas this change in y could be over any particular interval. Here's another way. So the derivative with respect to x of this function x, and this way is pretty uncommon. I don't even know if I've ever seen this particular notation, d subscript x of f of x, but d will refer to the derivative. And then as you get into more advanced calculus classes, you may see, or even in this class, we might see d over dt. F of t. So this is just where the function is written in terms of t instead of x. But whatever this variable is, that's the variable that we're taking the derivative with respect to. And as you get into, especially if you get into calculus 3, which is multivariable calculus, where you have functions of x and y, or functions of x and y and z, you can take the derivative with respect to any particular variable that you have. So, I mean, this is getting off topic a little bit, but you could have f of x and y, where this is equal to x squared plus y squared. You can take the derivative with respect to x. You can take the derivative with respect to y, and so on. So get used to these notations. We don't need to know this for this class, but get used to these notations. This one is very common. This one is very common. You might see this. You typically won't see f of x, but you might see like d over dx and then some function like that. But for sure, these two are the most common. Okay, so we've talked about in the last chapter, the last couple of sections of chapter 3, how do you find the derivative? And it was pretty tedious. And you can imagine if we have complex functions, like this is not super complex, but if you wanted to do the difference quotient and then take the limit as x approaches 0, finding f of x plus h and then minus f of x, this might be pretty tedious to simplify. Fortunately, somebody's already done general rules for these. So if you have a particular type of function, you can follow these rules, and they're almost shortcuts. They really are shortcuts. First one is the constant rule. So if you have f of x equals a constant, so f of x equals 2, f of x equals 5 halves, f of x equals 10, whatever it is. So f of x just equals a number. It's a constant function. Then the derivative of f of x is going to be 0. Now, why is that? Because if you have a constant function, f of x equals 2, That is a horizontal line. What is the slope of a horizontal line? The slope is 0, no matter where you are. So the derivative is 0. If f of x equals x to the n, any real number n, so n could be positive, n could be negative, n could be 0, n could be, well, n is not 0. I guess I should say any real number besides 0. N is not 0. If n is 0, then we have f of x equals 1. But anyway, positive, negative, fraction, decimal, square root, anything, any real number besides 0. Then the derivative is f prime of x equals n times x to the n minus 1. Now, this formula might look a little bit, if you've never seen this before, this formula might look a little bit intimidating, but it's really not. All we're doing is whatever this exponent is, we are bringing that in front, and then we're going to subtract 1 from the exponent. So, for example, if we have x cubed, f of x equals x cubed, the derivative, we're going to bring the 3 in front. So just bring that 3 down there, x, and then subtract 1 from the exponent, so squared. And that's all there is to it. So the derivative of f of x equals x to the n is found by multiplying the exponent n times x, and then decreasing the exponent on x by 1. So you subtract 1 from the exponent. So let's look at an example that might look complicated. It looks like it doesn't really apply to this, but it does. If you can ever write, so anytime you see an x in the denominator like this, if you can write it in the numerator, that is a better way to do it. So we can rewrite square root of x as x to the 1/2. Now, if we want to put this in the numerator, we're going to write it as x to the negative 1/2. So 1 over square root of x is the same as x to the negative 1/2. Now, if we want to take the derivative, this is just a power function. We have some x to some exponent that is a real number. Bring this exponent in front, so negative 1/2 x. Now subtract 1 from the exponent. Now, most of the time, and maybe never, I mean, it depends on you, I guess, but if it's just a positive integer exponent, you probably don't need to write 3 minus 1 and then on the next line. But if it's a negative, maybe in the beginning you need to, just to be sure you get that right. And you probably leave it like that. I would just be careful with the arithmetic. I mean, it's basic arithmetic, but you don't want to make silly mistakes with things like that. But that's all you do. So any x to any exponent, if that's all you have, then just bring the exponent in front, subtract 1, and there you go. And that's all you need to do for that derivative. All right, what if we have a constant times a function? A constant times a function. So f of x is k times some function g of x. If we want to take the derivative, then f prime of x is just going to be k times the derivative of that function. So the derivative of a constant times a function is the constant times the derivative of the function. So we're basically just ignoring the constant, just take the derivative of whatever that function is. All right, so case in point, y equals 3 square root x. We have now, again, probably write x with an exponent, so 3x to the 1/2. Now, dy over dx, which is another derivative notation. This is probably the second most common that you'll see, maybe equal to f prime or g prime. Now, let's just write, so it's 3 times the derivative of x to the 1/2. So 3 times, now take the derivative of x to the 1/2. So we have 1/2 x to the 1/2 minus 1. So that is 3 times a half, so 3/2 x to the negative 1/2. And if you like, I didn't do that up here, but you can write this as 3 over 2 square root x. That would also be fine. So either one's fine. I think my math lab is perfectly happy taking either one, unless it specifies how you should put your answer. But generally speaking, I think it's fine either way. Then the sum or difference rule. So this will allow us to take the derivative of a polynomial pretty easily. If we have f of x is the sum of two functions or the difference of two functions, and you can take the derivative of both of these functions, then f prime of x is just going to be u prime of x plus or minus, as the case may be, v prime of x. So the derivative of the sum is the sum of the derivatives. The derivative of the difference is the difference of the derivatives. So let's look at h prime, or h of t. So it's not a polynomial, but it is a sums and differences of derivatives to, or power functions, I guess you could say, the variable raised to some exponent. So let's write this where we have all the t's in the numerator and the t is to some exponent. So negative 3t squared we can leave. Let's write this as 2t to the 1/2. And then t to the 4th on the denominator. We're going to move to the numerator. It'll be 5t to the negative 4th minus 7. Okay, so this is just 4 different functions. And separately, we can take the derivative of each of them. And so that's what we'll do. So nothing complex here. So h prime of t. Now, notice you don't really have to, so we go back up to this one. You don't really have to do this separately. You can, because we ended up multiplying 3 times 1/2 eventually anyway. So you can just go ahead and multiply the exponent times the coefficient. So that's what we'll do here. So negative 3 times 2 gives us negative 6. T, subtract 1 from the exponent, so that's just t to the 1st. Plus, we're going to multiply 2 times 1/2, that gives us a 1. T, subtract 1 from the exponent, so 1/2 minus 1 is going to be negative 1/2. 5 times negative 4 will give us a minus 20. T, now subtract 1. Negative 4 minus 1 is going to be negative 5. And then the derivative of a constant function is just 0. So of course you don't have to write 0, but I will just so that we don't lose it. All right, so now let's rewrite this. Probably this is fine. Don't need to put 0, obviously, but probably this in my math lab will be fine. But let's write negative 6t plus 1 over square root t minus 20 over t to the 5th. Okay, so I didn't do many examples in this because I don't think it's helpful to do a whole lot of examples. I could do more, but I think it's more important. I think you need to do a lot. You really need to get to where when you see a function like this and you're asked to find the derivative, you do not have to think, because this, I don't know how you feel about it watching this video, just looking at it, but by the time you get to the next test, one like this needs to be just as easy as adding 10 plus 20. And the only way to get there is to practice and practice and practice, because we're going to learn rules for different functions, different types of functions. We're going to see exponential functions. We're going to see products of functions where you have, instead of uv plus v of x, u of x plus v of x, we're going to see u of x times v of x. So something like x squared times e to the x. How do you take the derivative of that? Or how do you take the derivative of x squared over e to the x? So these are all different rules that we're going to learn. And how do you take the derivative of a composite function? How do you take the derivative of a log function? So all of these things we're going to be learning. Each section will cover 1 or 2 of these. And so the next test is mostly going to be taking derivatives. So the more you practice it, the easier it will get. And to be a good, successful Calculus 1 student, Survey of Calculus student, you need to be able to take derivatives, and you need to be able to do it pretty easily and quickly, especially if you're going to move on to Calculus, Survey of Calculus 2. And any other math, derivatives are foundational for a lot of it. most of it probably what you'd see. So practice as much as you can and get to where it is just as easy as solving a basic equation or adding numbers or anything else. So, and you can do it. I promise you can.